Okay everybody, this is a continuation of my last video in which we were discussing correlation, scatter plots, and best fit lines, okay? And the intentions for us wanting to use best fit lines with scatter plots, okay? So in this video we're going to focus specifically on finding the equation of the line that we're calling the best fit line. That is if we had a set of data, and let me pop open here because we're going to be flipping back and forth in this video, but I've already made some scatter plots. You can see here this is a wonderful scatter plot in which we have what we would call a positive correlation. Positive because as x tends to increase, our y is tending to increase in a certain fashion, and we could draw a best fit line to basically describe what's going on with the data. We want to find the equation of this line, however, and recall that our intent for finding the equation of this line is because we would like to use the equation of that line to predict further values in the data set for which we did not have data. We want to be able to predict what would happen, say, beyond the data or in the future, if you will, or maybe we could even use that line to predict some things in between our data points that we didn't have data for, okay? So we call these respectively extrapolation and interpolation, and by the way, you don't need to know that, or if you want to know it, then you should know it. But anyways, the bottom line is this: if we need to find the equation of a line, then what's going to be the case? Well, we're going to need to know two things, and this is going to be like our workspace here. But we would like to know how to write the equation of a line, first of all. So we've got some necessarily really convenient formulas to use here, but we say y equals mx plus b. Now this is slope-intercept form, or slope y-intercept form of a line, where of course m is our slope and b is our y-intercept. Of course we know this. But if we knew, say, the y-intercept of our line and the slope associated with it, then we can just write the equation of the line in slope-intercept form. I will tell you this is probably not gonna happen. Probably not gonna happen. And the reason why is because when we write the equation of this line, when we make the line, chances are you're not gonna know the y-intercept. Okay, just probably not gonna know it. And also this slope. We're probably gonna need to know 2 points in order to find the slope through this line. So the formula we want to be using is what we call point slope form of a line. I have the hardest time writing on this thing. Point slope form of a line, which would indicate we're going to need to know two things if we're going to use point slope form. We need some point on the line. We'll call this point x1, y1, and we need m. Okay, so let's write ourselves a little note here. If we're going to use this, this is what we need. This is what we need when we make our line. Okay, so we're going to need a slope. We're going to need a point on the line, but of course point slope form works like this: y minus the y value of our point equals slope times the quantity x minus the x value of our point. And this is something we use in algebra all the time to write equations of lines. It's really easy to do. You just need to know a point on the line and the slope. So let's go ahead and flip back over to where we were previously and look at our positive correlation here. So in general, I can tell you this, and I saved us some time. Basically, a lot of the times in math, you'll be asked to make a scatter plot, okay? And the scatter plot's already been made for us here. You can see these are points up here on the left. This would be like our x's and y's. But what we want to do is now make our line of best fit. So here's how this is going to work. Actually, let's go ahead and let's write out the method for finding the equation of a line. Actually, that would be really good to do. So step one is make our scatter plot. Okay, which has already been done for us in my examples today. Make our scatter plot. Step two is going to be this: draw the best fit line. I'm putting this in here for anybody that would be taking notes. Best fit line to the best of your ability. Okay. Step three is going to be this. Now find 2 points. 2 points very nearly on the line of best fit. Okay, so they don't have to be exactly on there, but very nearly on the best fit line. And I want to make a note on this one, best fit line. We're going to find 2 points, and that's going to help us find the equation of this, essentially. But these, let's do it in a different color, don't have to be part of the original data set. Okay, don't have to be included in original data. What I mean by this is, sorry, it's hard to talk and write at the same time, in original data. The fact of the matter is this: we don't have to use, for example, let's go back over to our scatter plot here. We don't have to use any of these original points up here on the left. That's not a requirement. We can actually just choose 2 points that are convenient for us. So let's go ahead and proceed with making our best fit line here. I'm going to just make a random line, and then I'm going to adjust things around a little bit. So maybe we could drag this through here. Now recall that, well, now I botched this up a little bit. Let me try this again. I'm not using my mouse, I'm using my stylus. We'll put that down. Click. Okay, so recall that our best fit line here, it's not necessarily the case that you would connect the first and last dot on the data set, because look, when I do that here, point A to point J, necessarily, you'll notice that all my data points are on top of the line. So don't get into the habit of saying, oh, my best fit line, it's got to be, connect the first and last dot. We just basically want to make a line that splits the data about evenly, and kind of gives us the gist of what's going on with our data set. Okay, so this would be necessarily a pretty good best fit line right here. It kind of describes what's going on. Now we want to find the equation of this line, and the reason why is because, hey, if we knew the equation of this line, we could start to say things like, well, if the pattern of our data were to necessarily continue, then maybe we could find out where our data would have been if, say, x was 10, for example. It'd be somewhere like right here on the line. Or we could say even, hey, if the y value was ever to be 11, which is up here, we could trace that over to the line and say, well, then x must have been somewhere, if we trace this down, somewhere between 12 and 13, for example. And that's what we really want to do with this line. So to find the equation of this line, recall that we said, okay, so we've made our scatter plot, we draw our best fit line. Step 3 is going to be this: find 2 points that are very nearly on the best fit line. And we're going to choose points, if at all possible, that are extremely convenient. So I'm going to get my point tool out here, and I'm going to say, well, do I see the line crossing at any, where my grid crisscrosses? And so we'd say, okay, so this point right here, actually point C, it looks really close to point C, but even better, it looks close to this point 2, 2. Okay, so 2, 2 is like, in this case, we'll go ahead and quarantine all this data over here, all this stuff here. We say 2, 2 looks like it's on my graph. What else? Okay, so 2, 2 looks like it's on there. Let's find another point that's really nearly on there. I say, well, up here, kind of around I and J here, it looks like the point 9, 8. 9, 8 was very, very close to being on my graph, so that would be a convenient point to use. 9, 8. The bottom line is this now. We have 2 points on the graph. We need a point, just one of those actually, and a slope. Currently, we do not have a slope. So here's what we'll do now. Step 4 over here is, once we find 2 points, we'll go ahead and write this. That's interesting. It's very dark. Find the slope between the 2 points. Between the 2 points. Okay, we're going to use that slope. We're going to use that slope then to choose one of our points and our slope to write the equation of the line. Write, I'm writing very poorly. Write the EQ of the line. Okay, this is all very truncated work on my part. So let's go ahead and let me see if I can't fix the opacity of this here. No, it doesn't want to work with me. Anyways, so we've got our 2 points. Let's go ahead and find the slope of the line between these 2 points. So, change in y over change in x, our slope formula. So we say, okay, so 8 minus 2, and 9 minus 2 on bottom. So the slope of our line is very, very roughly 6 over 7. So about almost 1, so 6/7. So we have our slope. Okay, slope is 6/7. Now we just need a point before we can use point slope form. So of these 2 points, we get to choose either one, 2, 2, or 9, 8, and it's very convenient to use the point 2, 2 if it doesn't matter, because it's just smaller numbers. So let's go ahead and write our point slope formula here. We have y minus y1 equals slope times x minus x1. So now inserting the points we have here, we said slope we just determined was 6/7. That goes right there. Okay. We set our point, the y value of our point was 2, and the x value of our point was 2. So from here, we can just go ahead and distribute this. We have y minus 2 equals 6/7 times x. minus 12 sevenths. And the last thing we need to do is just add 2 to both sides here. So plus 2, and we'd get, let's kind of bring our work over here. So instead now we have just y on the left, just y. We still have equals 6 sevenths x. And then for example, you know, like 12 sevenths is negative, so we can do some side work here. Negative 12 sevenths plus 2 wholes. We're adding 2 here. If we take this times 7 on top and bottom, we get 14 sevenths, and we're adding that to negative 12 sevenths, so that's just a positive 2 sevenths. So now, what we're saying is this is the equation. This is the equation of our best fit line approximately. What I'm going to do is I'm going to go back over to GeoGebra now and type in 6 sevenths x plus 2 sevenths is our line, and it should be very, very close to this line. So we say y equals 6 sevenths x plus 2 sevenths. Now when I hit enter, boom, look at that, like really, really close to the line that we had originally sketched. So using that line now, you know, we could say, okay, so what if we made x equal to 10? That is, on our picture we say out here at 10, when x is 10, it would trace up and hit our line about where, because maybe we're interested in saying where would the data have continued on to at that point since we don't have data for it. Okay, so what we can do now is we could say, all right, well, if x is 10, x is 10, then y would have been what? Well, what this means is we're just going to go ahead and plug this in for x. We say y equals 6 sevenths times 10 plus 2 sevenths, and we end up with 60 sevenths, that's 6 sevenths times 10, plus 2 more sevenths, and that's 62 sevenths. Now, just to, you know, kind of let you see this here, 62 sevenths, we'll go ahead and find that. 60 on, hopefully. Oh, my network's slowing. Okay, so 62 divided by 7, you see, is about 8.85. So now going back over to our graph, at 10, okay, where would our data have been at 10? And so using our line, we were able to say, well, according to the line, it would have been about 8.85, which if you trace it over here is really, really accurate. Okay, so that allowed us to kind of predict where it would be in the future. So this was an example of doing it with a positive correlation. In the next video, we'll do one with, say, a negative correlation. Okay, just kind of reiterate the process here, as well as show you what would you do if there was, like, say, really not a positive correlation and not a negative correlation, but relatively no correlation between the data.